Okay. So, next we go to the next topic in this course, that is matrices. Now, all of you have seen matrices in some form before. Matrix can be thought of as an arrangement of scalars. So, it is just a convenient arrangement of scalars, and this arrangement of scalars can be either in the form of a square matrix, or it can be in the form of a rectangular matrix. So, what does it look like? So, you must have seen matrices that look like convenient arrangement of scalars, and you can have an example 1 0. So, the scalars, these are the scalars, and if you want you can make them real numbers also, okay, and they are arranged in a suitable form, and this is called a matrix. So, instead of writing all these 12 scalars, we just call it a matrix A. Now, if you notice, now this has a particular arrangement of scalars, and these are called rows and these are called the columns. So, in this case this is a rectangular matrix. So, not the same number of rows as columns. This rectangular matrix. Okay, so this is a matrix where the number of rows and columns are not the same. On the other hand, you could have a matrix like 0, so this is called a square matrix. So, when the number of rows and columns are identical, then it is called a square matrix. Okay. So, now so here we have a very visual definition of a matrix as just a convenient arrangement of scalars. Each term here is a scalar. Alternatively, you can also have it can even be a complex number. Okay. So, you can have a matrix of complex numbers, you can have a matrix of integers, matrix of real numbers, and so on. Okay. And so far we have just defined it as this arrangement. Now, it is also useful to think of a matrix as an operator that converts a vector into another vector. Okay. So, this is another useful way to think of a matrix, and in order to do that we need to define how to multiply matrices. Okay. So, if you have one matrix A is equal to a matrix, now this has 3 rows, 1 2 3 rows, 1 2 3 rows, and it has 3 columns, Now, in order to multiply this matrix to another matrix B, so it is essential that the number of rows of B be equal to 3. So, B has to be 3 by anything, and it can be 3 by let us say 1. So, if it is 3 by 1, so it has 3 rows and 1 column. So, it could be, for example, this could be 2 1 0. Okay. So, it is important that if I have these two matrices, then I can define A into B. Okay. So, this is a matrix multiplication of the matrix A and the matrix B, and it is essential that the number of columns of A should equal number of rows of B. Okay. Now, so in such a case you can define A times B, but however you cannot define B times A, because the order of matrix multiplication makes a difference. So, in B times A, so A is 3 by 3, B is 3 by 1, and you notice that the number of rows of number of columns of A is equal to number of rows of B. But if you try B times A, okay, number of rows of B is so this is 3 by 1 and this is 3 by 3. So, this is not defined. okay, because these two are not equal. Okay. So whenever you want to multiply two matrices, you should always check to make sure that the number of columns of the first matrix is equal to the number of rows of the second matrix. Okay. Now, once you have this definition of matrices, then there is another way, another useful way to look at matrices. Now, in this way you can think of a vector as a column matrix. Okay. So, for example, a vector an n dimensional vector will be a column matrix of n rows. Okay. So, for example, if you have a two dimensional vector, okay, if you have a two dimensional vector given by as x comma y, you can think of this as column vector x comma x and y. Similarly, you can extend it to 3, 4, 5 dimensions, and the usefulness of this is that you can ask what is a general operator that acts on one vector. It acts on vector x 1 y 1 to give you a vector x 2 y 2. Okay. And one such operator is the matrix. The matrix 2. So this is a 2 cross 1. So if you think of this as a vector as a column matrix, so this is x vector is equal to x y, and this is the column matrix corresponding to x vector. So I can multiply by a 2 by 2 matrix on this 2 by 1. So if I do a 2 by 2 matrix multiplied by the column vector x, which is 2 by 1, then I'll get another 2 by 1 matrix. So if I multiply these two matrices, then the order of the resultant matrix will be a 2 by 1 matrix. Okay. And this is chosen so that the matrix product is defined in the following way. Suppose I have a matrix A and A2 1 or A1 m, A2 m, all the way up to A. So an m by n matrix has various elements defined in this way. Okay. And an m by n matrix can multiply another matrix of order n by r. Okay. So if the elements of B are represented as B 1 1, all the way up to B n r. Okay. So an m by n matrix A can be multiplied to an n by r matrix B, and the resultant matrix A times B is an m by r matrix. Okay. So what we will see is that A times B gives C, where C is an m times r matrix. Okay. So let us come back to this. We take a matrix A, which is a m by r matrix, multiply it with another matrix B, which is an n by r matrix, to get C, which is an m by r matrix. And if you want to find the elements of C, so if C has various elements, C 1 1, C 1 r, C 2 1, C m 1. So if your matrix C has all these elements, okay, then you you can write the ijth element of C is equal to sum over A I k B k I, sum over k equal to and A has n elements. So, k equal to 1 to n. Okay. So, you multiply the I 1 element with the B k 1. So, suppose you are looking at the first element of C. Okay. So, C 1 1 is equal to A 1 1 B 1 1. So, where k equal to 1 plus A 1 2 B 2 1, okay, plus A 1 3 B 3 1 plus all the way up to A 1 n B n 1. Okay. So, that is how you define C 1 1. So, C 1 1 is essentially this multiplied by this plus this multiplied by this plus this element multiplied by this, and so on all the way to this element multiplying this element. So, A 1 1 B 1 1, A 1 2 B 2 1, A 1 3 B 3 1, all the way up to A 1 n B n 1. Okay. Similarly, we can write all the other elements. Okay. Now, once you have defined this matrix multiplication in this form, then you can ask what does it mean to multiply a matrix onto a vector. Okay. So, if you multiply a matrix with a vector, for example, if you have a 2 by 2 matrix A 1 2 A 2 1 A 2 2. If you take this matrix, if you take a 2 by 2 matrix and multiply it to a vector. So, if A is equal to this and x is equal to x y, okay, then A x, so this is 2 by 2, this is 2 by 1, A into x, A times x, this should be a 2 by 1 matrix, and the elements of the matrix are A 1 1 x plus A 1 2 y, A 2 1 x plus A 2 2 y. Okay. Okay. So, what we find is that if you operate a matrix on a vector, you get another vector. Okay. So, this is a 2 by 1 matrix. So, this is also a vector. Okay. And the components of the vector, the first component is a linear combination of these two of the components of the original vector. Similarly, the second component is also a linear combination of the components of the original vector. So, therefore, a matrix is a linear operator. So, this implies that matrix is a linear operator. Okay. So, if I multiply a matrix on the sum of two vectors, it will be the sum of the matrix multiplying the vectors. Okay. So, we have seen two useful ways of looking at matrix matrices. One is in general as an arrangement of scalars. The other is as an operator acting on a vector to give you another vector, and such an operator is a linear operator because the components of the resulting vector are linear combination of the components of the original vector. Okay. Now, one of the most important motivations of matrices and the use of matrix is in solving a system of linear equations. What do you mean by a system of linear equation? Suppose you have three unknowns x, y and z are unknowns. Okay. Now, a system of linear equations would be various equations involving x, y and z. So, for example, you can have a 1 1 x plus a 1 2 y plus a 1 3 z is equal to b 1, a 2 1 x plus a 2 2 y plus a 2 3 z is equal to B 2, okay, and so on. You could have this. So, you could keep having this for as many as you want. Okay. So, for convenience, let us take a third one. Okay. Now, this immediately reminds us of matrix multiplication, and it is not hard to show that this can be written in this form. T1 okay. So, you can write it in this form, and so here lies utility of matrices. So, system of equations, I can write it in a simple form. If I call this B vector, call this x, I can just write A x equal to B. Okay. A matrix A multiplying a vector x to give you another vector B. Okay. So, this whole system of linear equations can be written in a very compact form, and it turns out that various properties of this system of linear equations are related to the properties of the matrix, as we will see very soon. Okay, before we go into a little more detail at this system of linear equations, let us mention one thing, that if I take matrix all, if I take an n by m matrix, okay, so this has n rows and it has m columns. So, if I take a matrix like this, and if I consider the set of all matrices of order n by m, okay, this set of all matrices forms a vector space. Okay. So, this forms a vector space. So, and the reason that it forms a vector space is because addition of matrices is defined by this way. So, you have to define addition of matrices. So, addition of matrices, if you have one matrix A plus B, and two matrices A and B can only be added if they have the same dimensions. So, if this is m by n, this is m by n. Then this is a matrix C, which is also an m by n matrix, such that C I j equal to A I j plus B I j. Okay. So, the addition of matrices is term by term. Okay. So, the way you add two matrices of order n by m will form a vector space. Okay. And you can easily show that that this will contain the 0 matrix. The 0 matrix is the matrix with 0. So, you have n elements here, m elements here. So, the 0 of order m by n will just have zeros everywhere. Okay. So, a matrix with zeros everywhere is the 0 matrix, okay, and this is the identity matrix for addition of matrices. Similarly, the inverse of any matrix, okay, is also defined. So, if you have a matrix A is equal to A m by n is given by terms of the form A I j. Okay. So, A m by n has various elements like A I j. Okay. For example, if A11, A12, A13, etc., then minus A is also an m by n matrix, where the terms are instead minus A I j. So, you just take negative of each of them. So, just as you had vectors and you had the negative of a vector, you can have matrix and you can have the negative of a matrix. Okay. And this should be obvious, because vector is a special case of a matrix with just one column. Okay. So, in this notation, vector is a special case of a matrix with just one column. Okay. So, now next what we are going to see is a very important application of matrices, and in order to do this, we will define something called the rank of a matrix. So, before we define the rank of a matrix, let us mention one thing in brief, that another way of looking at a matrix is like think of a matrix as a series of as a set of rows vectors. So, matrix equal to set of, okay, and these vectors can be either column vectors or they can be row vectors. So you can think of either each row as a vector or each column as a vector, or you can think of a matrix where each row can be thought of as a vector. Okay. So the matrix can be thought of either as a set of vectors, and you can think of either each row, each column as a vector or each row as a vector. Okay. So you can think of this matrix as 4 vectors. So, for example, if you have a matrix 3, 2, 1, you can think of 3 vectors, you can think of it as composed of 3 vectors. Okay. And now that you have these 3 vectors, you can ask questions about, are these vectors, you can ask questions about the relation between these vectors. In particular, one question that will be relevant is whether these vectors are linearly independent or they are linearly dependent. Okay. So, for example, if you take these 3 vectors, are they linearly independent or are they linearly dependent? Okay. So, and this allows us to define something called the rank of a matrix. To number of, or rather the number of linearly independent rows or columns. Okay. So, the rank of a matrix is you look at the rows as vectors and you ask how many of them are linearly independent. Alternatively, you can look at the column of a matrix and you can ask how many columns are linearly independent. Okay. And it turns out that it's not hard to show that whether you look at row or column, you will get the same answer. Okay. And this answer is called the rank of a matrix. So, for example, in this case, for this matrix, you see that these 2 rows are identical. Okay. Since these 2 rows are identical, these 2 vectors are not linearly independent. Okay. However, these 2 vectors turn out to be, it is not hard to show that these 2 are linearly independent. Okay. So, the rank equal to 2, equal to 2. So, the rank of this matrix equal to 2. So, here I should say rank equal to 2. Okay. So now if you had instead chosen to work with column vectors, so if you had chosen to do it by column vectors, you would say 3, 7, 3, 2, -1, 2, 1, 2, 1, and let us see, it's not it shouldn't be hard if I multiply. So, you take 1, 2, 1, you have 2 -1, 2, and 3, 7, 3, and it shouldn't be hard to show that that these 3 are actually linearly independent. Okay. So, you should be able to construct linear combinations of these. You should be able to express one as a linear combination of the other. Okay. So, for example, you should be able to write 373 is equal to some constant into 2 minus 1 2 plus some other constant into 1 2 1. Okay. And let us see, if I take this as 5, then this should be 3 5 3. Okay. Okay. So, you should be able to determine these constants by choosing suitable linear combinations of these. So, whether you and this exists for some so you can determine constant c and c prime such that this equality is satisfied. Fine. Okay. So, the rank of a matrix is the number of linearly independent rows or columns. So, the point is, now by suitably choosing values of c prime and c, you can get this equality satisfied, and it is not hard to show that what should be the value of c prime should be nothing but 17 by 5. Okay. And then this can be c can be shown to be minus 1 by 5. Okay. So, then this is minus 2 by 5 plus 17 by 5, that is 3. Okay. Similarly, this is also minus 2 by 5 plus 17 by 5, that is 3, and this will work out to 1 by 5 plus 34, that is 35 by 5, that is 7. Okay. So, then you can show that these 3 column vectors are not linearly independent, they are in fact dependent, and you can also show that the rank of the matrix is equal to 2. Okay. So, the rank of the matrix is the number of linearly independent rows or columns, and suppose I consider a matrix where the number of rows and columns are different. Okay. So, suppose I consider a 4 by 2 matrix. So, if I consider 2 minus 1 3 0 4 minus 1 7 1. Okay. Now, the number of linearly independent columns is 2. Okay. So, if you look at columns, then you cannot have more than 2, and in fact these 2 columns are in fact linearly independent. Okay. What about the number of rows? How many rows should be linearly independent? And it is not hard to show that since each row is just a 2-dimensional vector, the maximum number of linearly independent 2-dimensional vectors is 2. So, and in fact it turns out that there are only 2 linearly independent vectors in this set. So, whether you look at rows or columns, the rank of the matrix is identical. So, the number of linearly independent rows and the number of linearly independent columns of a matrix are the same. Okay. So, how do you use the idea of rank of a matrix? And the most important application of the use of rank of a matrix is in solving a system of linear equations. So, let us say you have a system of m equations with n unknowns. Okay. Now, we will call the unknowns, we will call the n unknowns as x 1, x 2 up to x n. Okay. Now you have m equations involving these n unknowns. So, the most general linear equation will be a 1 1 x 1 1 n x n is equal to b 1, and you have a set of m such equations x 1 okay. So, you have n equations and m equations and n unknowns, and the question is, you are asked to solve and find the values of all the variables x 1 to x n. Okay. Now, the first question you will ask is, can you solve these? Can you solve these set of equations? Okay. And if you can solve it, then the next step is to actually go ahead and solve it. Okay. So, let us look at some specific examples, and then we can look at the details. Okay. So the first thing you will say is that since I have n unknowns, okay, if I want to solve it, typically I should have n equations. So if I had n equations and n unknowns, then I would be able to solve it. So these, you would say it can be solved if m equal to n, and this is the first guess that you will say. Okay. So now let us look at some examples. If m is greater than n, then we say that then you will say that I have too many equations and too few unknowns. So it may or may not be solvable. In some sense I have too many conditions and too few unknowns. So actually the system you say is overdetermined, whereas if m is less than n, you say that I have too few equations, so I cannot solve for all the variables. Okay. But let us look at this in a little bit more detail with specific examples. Okay. So let us look at a case where m is greater than n. Okay. Or first we will start with the case where m is equal to n. Okay. So the question is this true? Okay. So suppose I take the equation x plus y equal to 4, and I will say 2x plus 2y equal to 8. So I have two equations, I have two unknowns, but if you try to solve it, you can immediately see that you cannot solve this set of equations. The reason is that if I divide by 2 here, I get back the same equation as I started with. Okay. So m is equal to n, but cannot solve. Okay. So next let us consider another system of equations. Let us say x plus y equal to 4, 2x plus y equal to 5, and we have a third equation 0. Okay. So we have these. So now we have 3 equations and you have only 2 unknowns. Okay. So in general you would say that this is an overdetermined problem. Okay. So what happens in this case? Let us say you take the first 2 equations, and the first 2 equations, when you look at these two, you will get x equal to 1, y equal to 3. Okay. Now when you substitute this in the third equation, you do not get an answer. So not satisfied. In other words, what you say is that the third equation is not consistent with the first 2 equations. So you say that these 3 set of equations are not consistent. Okay. So let us come back to these 2 equations. Now these 2 equations, I said that you cannot solve them. Okay. And in this case we say that the third equation is not consistent with the first. Now when you say you cannot solve for them, suppose I take x equal to 10, then y equal to minus 6 will satisfy both the equations. So for any value of x, I can find a value of y. So in other words, there are infinitely many solutions, infinite solutions in this case. Now in this case, it is not you can never find. So this has no solutions. On the other hand, if you just had the first two equations, this implies this has unique solution. This is unique solutions. Okay. Now, so we seem to have a set of equations where m is either equal to n or m is greater than n, but in each case you have different characteristics. In one case you have infinitely many solutions, in the second case you have no solutions, and in the third case you have a unique solution. Okay. Now, if m is less than n, for example, if you have x plus y plus z equal to 3, 2x plus 3y plus z equal to 5, okay, and or let us make it, let us make it 5. So here you have 3 unknowns and 2 equations, and you say that you cannot solve this. In other words, if I pick one value of z, then I can always find a set of x and y. Okay. So again this cannot be solved. Okay. So this cannot be solved, but suppose I set x equal to 1, suppose I take x equal to 1, then I have y plus z equal to 2 and 3y plus z equal to 3. Okay. And these two equations can actually be solved. Okay. So these two equations can be solved, and you can get solutions. So for example, take x equal to 1, then you get y plus z equal to 2, okay, and 3y plus z equal to 5. So in other words, you will get 2y 3y plus z equal to 3. So then y plus z equal to 2, 3y plus z equal to 3. Okay. So you can conclude that y equal to 1.5 or equal to 0.5, z equal to 1.5. Okay. So this is a solution. So this solution holds when you take x equal to 1. Similarly, you can take any value of x and you can solve this, and so in other words, you would say that there are infinitely many solutions. Okay. So basically it seems from all this argument that that your original idea that the number of equations should be equal to the number of unknowns is not a complete idea, because in some cases you can solve it if the number of equations and unknowns are the same, you can solve it. In some case you cannot solve it, in some case there are infinitely many solutions, and there seem to be too many cases, and this simple criteria that number of equations and unknowns should be the same does not seem to hold in general. Okay. And so this is where the rank of the matrix comes into play, and what we notice is that when you said that these two equations, they cannot be solved even though number of equations and unknowns are the same, we notice that these two equations are completely linearly dependent. Okay. So this equation is just twice this equation, okay, and in a sense you have only one independent equation, and in this case what happened was this equation was not consistent with these two. Okay. So that is another case that we have to consider, and finally in this case these two equations could be solved because you have two equations and two unknowns, okay, and so on. Okay. So let us see how to state this in very simple way. Okay. So now I am writing my system of equations. So if I have a11 x1 plus a12 x2 a1 n xn, and I go all the way to am1 x1 am2 x2 AMN xn equal to BM, this is equal to B1. So, if I have a system of equations of this form, then I call this, I can write this in the form A x equal to B, where A is this matrix of coefficients. So, A is A11, B A21, all the way up to AM1, AM2, AMN. So, this is my A matrix. Okay. X is x1 up to xn, and B is B1 up to Bn. Okay. So, now what can we say about this system and the solvability? So, the first thing we will say is that solutions exist if rank of A is equal to rank of A tilde, where A tilde is called the augmented matrix, and this has coefficients. So, it looks like A11, A12, A1n, and then you put B1. Okay. So, what you do to construct this matrix is you take this vector and put it here. Okay. So, you have a m cross n plus 1. So, there are n plus 1 columns to this. So, this had m cross n, this is n cross 1, n cross 1. Okay. So, what you did is you took this whole B matrix and you attached it to the side of A, and you created this larger matrix to A2n B2 all the way up to okay. So, now the first thing you say is that the solutions exist if rank of A equal to rank of A tilde. So, only in this case can the solutions exist. Okay. So, if this is not true, then it means that these equations are not consistent with each other. Okay. So, if this is not true, then the equations are not consistent with each other. So, if this is true, your equations are consistent. Okay. So, if this is true, then the equations are consistent, and this is a necessary condition for any solutions to exist. Okay. So, probably I should write this as, so right way to say this is solutions can exist only rank A equal to rank A tilde. So, the first thing is that whatever equations I give should be consistent with each other, and that is true only if rank of A is equal to rank of A tilde. Okay. Now, if rank A equal to rank A tilde equal to m, if rank A is equal to rank A tilde is equal to the number of unknowns, this is the number of unknowns, or okay, sorry, this I should read, yes. Okay, or rather it should be n number of unknowns. Okay, then unique solution exists. third thing is, if rank A is equal to rank A tilde and this is less than n, okay, then infinitely many solutions exist. Okay. So, the rank tells you the number of linearly independent rows or columns. So, if the rank A is less than n, that means you have less than n independent equations. So, that means you can have infinitely many solutions. Okay. So, in a very simple way, using the concept of rank, you can find out in which case are the equations consistent, or which is what is necessary for solutions to exist, and you can find out whether you have a unique solution or you have infinitely many solutions. Okay. And it's not hard to show that since the number of rows of A is equal to n, the rank can never be greater than n. Okay. So, rank of A can never be greater than n. Okay. So, you can never have rank of A greater than n. So, we will just put a note saying that rank of A has to be less than or equal to n. So, this is by definition. Okay. So, this is a note. Okay. So, you only need to consider what happens if rank A is less than n and what happens if rank A is equal to n. Okay. And the condition for unique solution is that rank A is equal to rank A tilde equal to n, and otherwise you can have infinitely many solutions. Okay. So, the rank really tells you about the solvability of a system of linear equations, and this is actually one of the most used concept. You in various problems in chemistry, you finally end up formulating your problem as a set of linear equations, and then you look at the solvability based on the rank. Okay. So, we have talked about the rank, and we have said how the rank can be used to tell whether a system of equations has a solution or not. Now, two questions remain. One is okay, the rank tells us whether you have solutions or not. Now, what is the best way to determine the rank of a matrix? Okay. So, what is the best way to determine the rank of a matrix? Well, you said that we have a set of vectors, and you have to determine how many of them are linearly independent. Okay. And it turns out that there are some good ways to determine the rank of a matrix. Second thing that remains is that suppose there exists a unique solution, then what is the unique solution? Okay. So, what is the solution? So, these are the two questions that we will consider next. Okay. So, let us start with determining the rank of a matrix. So, if you are given matrix A, to 1 A 1 n, and this is 2 n, A m 1 A m 2 up to A m n. So, you have a matrix, an m by n matrix, and you are asked to determine its rank. Okay. So, the first thing you see is which is so you have to find out how many rows or columns are linearly independent. Okay. Now, if m is less than n, okay, that means the number of rows is smaller than the number of columns. That implies rank less than or equal to m. Okay. So, then what you can do is you can take each of these rows and you can find out how many of them are linearly independent. Okay. So, you can take all these rows and find out how many of them are linearly independent. Okay. Now, this in general, it can be a very tedious operation. You take you essentially take linear combinations of these rows and set it equal to 0, and then you go through the usual process of determining linear independence. Okay. Fortunately, there is a more elegant way to do this, and this is by a process called Gauss elimination. and this is a and the reason for using this, we will discuss this in the next lecture, but the reason for using Gauss elimination is that suppose you take all these vectors and you look for linear independence. If they are all linearly independent, okay. So, if rank is less than m if m vectors are linearly independent, rank equal to m. However, if they are linearly dependent, if are linearly dependent, rank less than m. Okay. So, all you can say is the rank is less than m, but you do not know what is the value of this rank. Okay. So, so then you have to consider various subsets of vectors and see how many of them, what is the maximum number of them that are linearly independent. Okay. So, you go through this procedure, and if you have large matrices, you can see that this procedure can get a little tedious. So, there is a more elegant procedure called Gauss elimination, which we will discuss in the next lecture.